Hello, and welcome to the first lecture covering Chapter 5 from the Physics of Everyday Phenomenon, a Conceptual Introductory to Physics. This is the 10th edition by Griffith and Brosing. So, what we're going to do is we're going to start talking about circular motion. Now, in this video, I'm just going to talk about everyday terrestrial circular motion. Things spinning in circles, get some definitions out of the way. That's going to correspond to sections 5, here we are, Chapter 5, Circular Motion, 5, 1, and 2. All right, sections 5, 1, and 5.2, 5.1 and 5.2. Then we're going to stop because that's a natural breaking point in the chapter. And in the next video, or two, hopefully one, kind of keep it more concise, I want to talk about planetary motion. Because you can see 5.3, planetary motion, 5.3, Newton's law of universal gravitation, which applies to more than just planets, but helps us understand the motion of planets, which is a wonderful starting point of all of this large-scale gravitational motion. And then looking at the moon and other satellites, thinking about how there's a direct relationship between velocity, altitude, is some really fascinating things. For example, if you want a satellite that goes slowly, that has a period of orbit that, say, is equal to like the length of a day, well, then you need that satellite to be incredibly high up compared to most satellites and compared to what's called low Earth orbit, which is just beyond the atmosphere. We're talking, 20 times further. So very interesting ideas in terms of how satellites work, how fast they go or how slow they go, and what it means to be in deep space and how far the moon is, for example. Okay? So those are all the ideas that we can quantify using physics, using the building blocks that we have been building, for lack of a better word, up until this chapter, because before this chapter we defined motion and we defined forces, okay? And so we're putting those ideas into play. And what's interesting about this is that we can take this approach that we can study planets, and we can do it without really talking about energy, because in chapter 6 we will actually officially introduce and define energy and some other really important ideas in physics, namely momentum. So we kind of have these ideas that physicists keep going back to, their go-to key concepts, right? Well, likewise, that's what we're doing here, but we're able to build something with fewer building blocks. And I guess my point is, historically, that's what happened. People started asking questions about the celestial sphere, trying to understand the motion of those wandering stars that we now know as planets, before we got to a point where we understand things like conservation of energy in terms of of engines and repetition and power and output and things that maybe we take for granted because of the Industrial Revolution and later our understanding of electricity and magnetism. But all of this understanding of planets predates that. And so it really makes sense to present this now, because I think sometimes following history is a good way of understanding the subject. So you find yourself not understanding physics, sometimes go back to the history, right? There are a lot of good videos and books that talk about the history of physics. But all that aside, we're now going to talk about circular motion, and we're not even going to talk about the planets in this video. But we care about circular motion. If you want the aha moment, it's because of things like understanding the orbit of the moon. Right? The fact that the moon is in free fall, quite literally, but it's moving so fast to the side that it never hits Earth. Why do things even end up in these situations? Why is that the same story for planets, right? And then how does this apply to understanding, things like what engineers consider when they build a road, making sure that you don't swerve out of control, that the curvature of that road, this looks like a pretty steep one in the slides picture, right? That curvature of the road isn't so steep, or it's compensated for with a certain amount of banking so that there's the correct force to keep you not in orbit, but basically the same forces. Because gravitational force for an orbiting body like the moon around Earth, well, that's a centripetal force. Plain and simple. And it's the only force in that system. When the car is going around the turn, there's always going to be some drag force, and that has some effects, right, that you actually don't have to worry about with planets. Thank goodness, right? Planets had drag, they'd be crashing into each other all the time. But with the car, you're pushing against that drag, you're pushing through the air, but the big force that's going to keep you on the turn, keep you from speeding out of control, like in that picture, is going to be the same force, centripetal force, right? It's going to be created by friction, perhaps some normal force in the case of a banked turn, but it's the same force. So we see that the centripetal force is actually the name given to any force that maintains circular motion. The centripetal force itself is not a force in its own right. If you said, oh, it's a centripetal force, and then someone asked you, well, but what force is it? Well, you'd have to answer the question, because there's always some force that creates the centripetal force. It can be the gravitational force, it can be the normal force, it can be the electrostatic force, it can be a magnetic force, it can be a friction force, it can be a buoyant force even, okay? It can be a tension force. So there's so many different named forces, some that are fundamentally different because they're a fundamental force, others just because they're common forces like tension and normal force and buoyancy, okay? So, I think you get the point. This is all circular motion. And centripetal force is a big part of it. If you understand what centripetal force is, you are well on your way to understanding circular motion. So, let's build up to that. So, first a concept question. A ball is whirled on the end of a string with constant speed. When the string breaks, what path will the ball take? Right? Think about what you know about Newton's laws of motion. What was maintaining the circular path? When the string breaks, is that gone? And if that's the case, what does Newton's first law tell you? Newton's law of inertia. Okay? It tells you that the ball must maintain the instantaneous direction of motion, known as its velocity vector, at the moment that its force was eliminated. Okay? The force that was maintaining the circular motion. Because you can't maintain the circular motion without a force. Why is that? Because circular motion is not acceleration-free motion. Circular motion is constant acceleration motion. Okay? Constant acceleration as far as the magnitude of acceleration. Because what it requires is a force that points straight towards the center of the circle, right? So right in the direction of my cursor, a force straight towards the center, and without that force, the circular motion is not maintained. Okay? And as soon as that force is gone, the velocity vector, which at that instant in time would have been pointing right in this direction, right, along that straight orange line, that dictates the further motion of the ball. Because once the string is cut, once the tension which was supplying the centripetal motion is eliminated, now there's zero forces in some sort of distant space where there's no gravity nearby and no electricity, right? Some perfect zero force situation. Just continues off, okay? Or maybe just continues off for a moment and then some other forces become dominant in its motion and maybe it just then arcs down to the ground with a parabolic motion of constant acceleration because it becomes a projectile, because maybe you're swinging it over your head, right? Okay. So, right, the string breaks, the ball flies off in a straight line path in the direction it was traveling at the instant the string broke, the direction of the velocity vector. If the string is no longer applying a force to the ball, Newton's first law, the law of inertia, tells us that the ball will continue to move in a straight line. That's exactly what the law of inertia tells us. It also tells us that bodies at rest will remain at rest, right? Because that's not a straight line per se, right? It's just staying at rest, okay? So that's the other case, right? So you got things stay at rest, no force acts on them, they'll stay at rest, okay? That's the law of inertia. Things are in motion, they'll stay in motion if no force acts on them, okay? Inertia is that resistance to change. So circular motion is called centripetal motion. It's the name of the motion, right? I named the force a lot, centripetal force. With the string providing the centripetal force. The string provides it. So now the word centripetal actually means center seeking. Okay, that's the root of it. So this force is seeking the center. So we know that from the free body, which is the ball, right? And the force vectors acting on that free body, because they don't just originate from nowhere, right? They point from the free body. Right? Well, those force vectors, in this case, there's only one. It's the centripetal force, it's the tension force, and it will point straight towards the center. Okay? So it'll be a force vector pointing straight from here towards the hand. That's the only force at play before the string broke. All right? So centripetal acceleration is the rate of change in velocity of an object that is associated with the change in direction of the velocity. All right? And it's quantifiable for perfect circles. It's quantifiable for ellipses, more complicated, and be changing, right? But here we just have this nice concrete value. Now, we're not deriving it mathematically, by the way, but if it turns out that the relationship is the velocity squared, right? Now, velocity has direction, right? It's a vector. When you square it, it doesn't have direction anymore. You've taken its magnitude and you've squared its magnitude, okay? So if it was moving around the circle at 20 meters per second, that would be both its speed and its magnitude, and the magnitude of its velocity, 20 meters per second. Because you're not giving it a direction, because its direction is constantly changing, right? Because it's moving around the circle, So that's its magnitude, 20 meters per second. You'd square it, in that case, 20 squared, 400, right? And then you divide by the radius of the circle. So the bigger the circle, the smaller the centripetal acceleration. You know that from a wide turn versus a tight turn. Where do you notice the effects of turning more? on the tight turn, right? So the smaller the value of r, the more noticeable the turn, which is to say the larger the centripetal acceleration, okay? So bigger r, smaller centripetal acceleration, smaller r, bigger centripetal acceleration. That's called an inverse proportionality, you know? That's the idea. One goes up, the other goes down, okay? But velocity is a direct proportionality, and it's a direct squared proportionality. So the faster you go around a turn, everything else held constant, the more the more you're going to feel that turn, the greater the centripetal acceleration. You know, so you go really fast around a turn, well, that's going to really scale up your centripetal acceleration because it's non-linear, right? You double the speed, you have quadrupled the acceleration. You triple the speed, and you've, well, multiply the acceleration by 9. Noon-tupled, I don't even know, what would it be for 9? Okay, but you get the point, okay? So that's the calculation. We'll do a quick example of that at the end of this video, okay? All right, so centripetal acceleration is the rate of change in velocity of an object that is associated with that change in direction. So it comes directly from that type of motion, just, you know, what we call uniform circular motion, because you're not slowing down or speeding up in the circle, you're just continuing in the circle at that constant rate, all right? And this is, you know, obviously outlined in the textbook as well, right? When we get into, you know, you have some examples, right? There's a force vector acting on the car going through a turn, right? Pointing towards the center of the circle. Centripetal, center seeking, right? And then you continue on, right? Here's an example of a banked turn. What creates the centripetal force in this case? It is a component of the normal force, all right? So it's not the entire normal force because it's angled. That's the whole thing about banking. It's just the part that points straight towards the center of the circle because it's selective. It will only be the part that points straight towards the center. Everything else will not apply towards actually the centripetal acceleration. It just supports the weight of the car, right? So the steeper the banking, then the more you're actually providing centripetal acceleration. But you might not need that much centripetal acceleration because think about how it's dependent on velocity. So if you want a turn that's really steeply banked, well, you'd only want that, or I should say you'd only want a turn that's really steeply banked if you're going to plan to take it at really high velocity. So that's why you only see those really, really steeply banked turns where? On racetracks, right? Because that's the only time that it actually makes sense. They're designed for such a high velocity. All right? And you know, steep turns can be pretty steeply banked too, I guess, for everyday traffic, but only on those mountain roads, and they still don't quite compare. Right? And then this is the idea that we can, you know, it's not just bird's eye view of turns going around, you know, for roads and going around, you know, mountains and so on. It also is a vertical view if we think of something rotating this way. And what's interesting about the vertical view is now gravity isn't just creating friction or creating the normal force. Now gravity is directly contributing to the sum of forces. In other words, when someone goes through a Ferris wheel, they're going to vary in their, well, effective weight. Their effective weight is how much they're pushing into the seat, right? So at the bottom of the Ferris wheel, right, they're pushing into the seat more. They feel extra heavy. Right? They'll feel extra heavy because they feel the seat pushing back more than it normally would. That's the sensation of feeling extra heavy. At the top, right? At the top of it, well, now they're actually going to feel light because now the centripetal force is going to be canceling out some of their weight. Not so much that they feel weightless unless the Ferris wheel is going incredibly fast, right? And it's spinning out of control, you know? But no, they just feel slightly lighter, right? And that would just be a repeated process, okay? Affecting the normal force. In the same way that the linear motion of an elevator, you know, that is slowing down or speeding up, going up or down, and how that can affect the perception of weight. Same idea, but now it's a cyclical circular change in the normal force, okay? So what is this actual value of the centripetal force and that can affect things like the normal force? Well, it's just m times the centripetal acceleration. Very convenient, right? So what we're doing here, what's kind of cool, is we're employing Newton's second law to immediately go from one concept, okay, a new way to express a particular constant acceleration, and then just immediately then having the force, right? So as long as we have this new form of acceleration, then we immediately have a way of calculating the force in newtons, right? And this new form of acceleration it's a particular situation in the same way that when we had those equations that applied to constant acceleration motion, and we had the equations for linear velocity and parabolic displacement. Well, in that case, that was just one particular situation, an important one, because it's like anything that's in free fall, negligible drag. Same thing here. We have just one particular situation, it only applies to circular motion. It doesn't apply to non-circular motion, if it's elliptical or if it's some other shape. It doesn't apply to, slowing down or speeding up within the turn. This assumes you have to maintain constant velocity for this to apply perfectly. But you can take snapshots in time if the velocity is changing, right? So then you find this the instantaneous acceleration rather than the overall. But even then, even with those limitations, it's so valuable because it's such an important starting point and such a common case, and all those variations on circular motion often can be approximated as circular motion. So now we have a simple mathematical form for a system that is going to be a key approximation for so many others. All right. So here is the idea of a centripetal force being created by tension. All right. So check it out. We're spinning something. This is something you can just tie a ball to a string and spin it around. We've probably all done this in some form, right? This is also the tether ball case. Just replace the hand with a pole, right? Tether ball like you play in elementary school. So you hit this ball, it starts spinning around in the circle. At some moment in time, if we were to capture it, right, and look at the sum of forces acting on that ball, it's on Earth, so it's experiencing a weight, okay? And then the other external force it's experiencing is this one, T, right? Ignore the ones to the subscript for now, because it's tension, right? Absolutely, because otherwise, it wouldn't do this, right? The whole spinning in a circle is dependent on the string. Without the string, it doesn't spin in a circle, right? So that's a big part of the force, okay? Well, it turns out that tension is doing two things, and those two things can be expressed as two components, which make a right triangle, by the way, right? One is the vertical component of the tension, and the other is the horizontal. V for vertical, H for horizontal. Well, the vertical component is just supporting gravity, so that's going to be dependent on how heavy the thing is. Bigger ball, that's going to kind of change the angles of the situation. Okay, it's harder to spin a heavier ball, right, in a tighter circle. It's easier to spin a really light ball in a tighter circle. Think about like tying a styrofoam ball to a string and spinning that styrofoam ball versus tying a steel ball to that string and trying to spin that steel ball. Which is going to be easier to spin nearly horizontally, right? Well, I'll tell you, it's a styrofoam ball, right? That's because you can easily get a much larger value here because your value or comparatively larger, because your vertical tension component is just inherently going to be small because it only has to match the weight. Small weight, small vertical tension component. So then this other leftover tension, what is it? Why is it even there? It's the centripetal force. Because this whole situation is dependent on spinning in a circle. You stop spinning from a circle, ball comes down. So that force maintains the shape, right? And it only maintains as long as you keep spinning it, but that's the case, and that's what you're going to see in the next video of planets. All this stuff is it only works if you keep moving, right? It only works if you keep flying to the side, right? Because this requires a maintenance of velocity, right? You have to maintain a certain velocity to keep this going, right? Well, that's what planets do. They're just constantly flying to the side at kilometers per second, and they're able to do this because space is essentially a vacuum, and these were high energy rocks that all came together to make the planets in the first place. But that's really what's happening. It's all these fast side to side motion, maintaining these shapes, maintaining circular shapes. Okay, so that's what we have here: a circular shape, maintained by velocity, maintained by a significant centripetal force, right? So the vertical component, right, is just equal to the weight. At higher speeds, right, that's the idea, right? The string is closer to horizontal because the larger horizontal component of tension is needed to provide the required centripetal force, right? That T sub H is a centripetal force, right? And you make V bigger, then, well, your centripetal acceleration is going to get bigger, recall, right? V gets bigger, AC gets bigger. If AC gets bigger, so does FC. AC is centripetal acceleration, FC is centripetal force. You need centripetal force to maintain circular motion. Okay, so centripetal forces. The centripetal force is the total force that produces a centripetal acceleration. The centripetal force may be due to one or more individual forces. I have said this, right? It could be gravity. It could be gravity combined with something else, right? Like a magnetic force, right? That happens with certain systems, kind of. But bank turns, it can be friction plus normal force. There's all kinds of combinations, okay? So the static force of friction is the frictional, or sometimes you say friction, but frictional is the adjective form, force acting when there is no motion along the surface, all right? No skidding or sliding. So that's a key one for turns because there's no motion in the direction that the force is being applied. You might be, wait, but the car is moving. Well, no, the car is moving in a different axis, right? And we only care about the sum of forces in what's called the radial axis. That's the axis that points, in towards the circle. So in the case of the car going around a turn, it's going to the book here, right? So we look at the direction of this force vector here. That force vector, right, both the ones coming from separate wheels, as was shown in the picture, those both point in the radial direction, okay? And those would be created by static friction forces. So we'll go back to the term. Those red arrows, they're representing friction forces, are none other than the static force of friction, all right? They're pointing straight in, and the wheels are not moving in that direction, right? The wheels are turning, but they're turning in the direction that's in and out of the screen. There's no movement in the left-right direction relative to the screen, relative to the picture, okay? All right, and then the kinetic force of friction is the frictional force acting when there is motion along the surface. So if the car starts to slip, at the moment it starts to slip, now you have the kinetic force of friction. You got a different situation to deal with, all right? And it also turns out you have different coefficient to deal with the different forces, because any like two surfaces that interact and all the different contributing forces that create friction, because that's not a fundamental force by any stretch of the imagination, it's created by lots of different things, well, then they inherently are going to be smaller for motion. So if you're already moving relative to that surface, it's harder to, say, slow down or stop. If you're stopped, it's easier to stay stopped, okay? So the kinetic force of friction is going to be a smaller force, everything else held constant. All right, so the friction between the tires and the road produces centripetal acceleration on a level curve, okay? On a banked curve, you can create it from just the normal force. So you could have a banked curve that is, you know, completely smooth, like icy, you know, but that would be kind of it'd be like a stunt, right? You could go around an icy curve that, you know, you'd imagine no car could drive on, and you could do it at just the right angle and just the right speed, so you literally don't need friction, right? But most of the time, banked curves are a combination of friction and the component of the normal force. And here, just like it was the component of the tension force that was horizontal that created the centripetal motion, well, we're being consistent with the way we draw our figures, and here we see it's the horizontal component of the normal force rather than the tension force, as it was with the ball and the string, right, back here. But now it's the horizontal component of the normal force creating what? The centripetal force. And that's it, right? All, you know, this much larger vertical component is not contributing to the centripetal force at all, right? So, you know, that maybe implies, you know, that's a certain speed. It also, you know, it's kind of realistic in terms of the high mass of the car, right? You don't need all of the normal force because, you know, you don't need that steep of a banking angle. But there'd still be some friction at play, right? And then as far as Ferris wheels, right, the weight, as I was saying, doesn't change. But the apparent weight, which is a term that isn't, you know, we don't have to use, but apparent weight is just how much you're pushing into the seat, right? So your apparent weight does not remain constant because it's not weight. It's not just affected by universal gravitation, which we'll talk about later in this chapter. It's not a force pair between you and Earth. Apparent weight is how much you are pushing into the chair. Okay, and that varies, okay? Just like in an elevator, it varies. As I was saying when we were looking at the figure in the book, right? Here on the slide, same idea. The normal force responds to that apparent weight, and that does depend on the position. Heaviest at the bottom in terms of the apparent weight, which means largest normal force, least normal force up at the top, okay? And that's what you feel, right? Because you feel the seat pushing back on you. So the normal force is your perception, right? All right, and then we'll talk about planetary motion in the next video or two, okay? So let me quickly turn your attention to a calculation. All right, so here what I want to put together is just a quick calculation that shows an example of centripetal motion. We'll have it be a ball spinning on a string. Okay, kind of the title. And if we were to look at this string, it will have a certain radius, okay? So this value here is r for radius, and attached to the end of it is the aforementioned ball. So we'll just drop that right on there. And then the ball will follow that circular path, which we can kind of probably sketch here, kind of throw off the side, make it look believable. Right, so it's following some sort of circular path on that scale, right? So that's going to be just its direction of motion, right, along that way, okay? And it has a velocity that doesn't change in value, right? Because that's the whole thing here. That's how we can just find one value of centripetal acceleration, because we know that the magnitude of velocity, the speed, is not changing. So V for this ball on a string is going to be 14 meters per second, okay? And then on the note of giving us values, the radius is going to be 2.1 meters, okay? So 6 feet long, you know, we're spinning something around. Then we have the mass of the ball is going to be 2.2 kilograms, okay, about 6 pounds. No, more like 5. Not great at doing between pounds and kilograms, so never mind. But that's all you need, okay? So what I want to ask you to do here is then to give me some values. All right, so what I'm asking for is, what is the centripetal acceleration of the ball? All right, so that's your question A. All right, and you can get started if you want, but otherwise hold tight, because I'll give you a hint, but you can pause and work without the hint. And the second question I want to ask is just, what is the tension? All right, what is, some space there, what is the tension in the string? Are we all clear on where the string is? I'm thinking maybe I should make that a little bit more obvious here. Actually, let's pull. Here, let's just take this and see if we can pull down the radius, kind of show it somewhere else. Right, because the whole idea of the circle, we can show it, and then I just want to then show the string as being right here, so you can have more clear on that. Right. So there's the string, and the centripetal force is none other than the tension, and that force has to point along the string, right? That's what sort of, you know, propagates the force. Excuse me there. And it has to point not only parallel to the string, but most importantly, perhaps, to the center. Okay? It points towards the center because the centripetal force points inwards towards the center of the circle. All right? And here, let me go ahead and put this over for a second so you can see everything. All right? And we can make this. I know what I should be doing here. This is not far enough over. All right. All right, so good. You can see the whole figure here. You won't need the calculations just a minute, but here it is. Okay. All right, so pause the video now if you'd like to attempt to answer these questions by referring to the formulas that you may know from the book or previously in the video. All right, so go ahead and attempt an answer. If you would like to, for me to show you the formulas, I'm going to show them to you now. Okay, so the formulas for A, or the formula that you're going to need, is that of centripetal acceleration, which is just v squared over r, uppercase R in this case. Okay. Likewise, the single formula that you will need for B is that the centripetal force, I should actually start with the tension force, which I represent by T, is the centripetal force by another name. Okay. It's the force that's creating the centripetal force in this case. And it's equal to, precisely, from Newton's second law, ma. In this case, that A is the centripetal acceleration, which means the centripetal force is just mv squared over r. All right, so if you're able to complete this problem by putting that all together, that's great, right? Because, you know, I hinted at this stuff, but it didn't, you know, exactly show this idea that it does become mv squared over r. It's just a substitution of the centripetal acceleration. Okay, right? So hopefully that helps. Plug in the values now, right? Make sure you can get values for yourself, and then compare them to mine, which I'm going to start calculating right now. Okay. So the first one for the centripetal acceleration, which we'll just label as A, that's just going to be v squared over r, or 14 squared, divided by, well, 2.1. No conversions necessary, okay? So we got a value of 93. This is a high centripetal acceleration. This is about 10 Gs, or maybe it's about 8 G, right? So this would be enough to knock someone out if you threw them in some sort of, like, you know, training wheel, like the astronauts experience, you know, some big, almost looks like an amusement ride from hell, right? Because it's this big, you know, arm that's spinning around, and you spun someone around at 8G, you would potentially, you know, cause bodily harm, and usually you knock someone unconscious. It's a huge amount of acceleration, right? Because you would be 8 times heavier, approximately, you know? All right, so that's our value, though, and this is our you know, incredibly fast moving ball on a string, right? Because 14 meters per second is, you know, 40 miles an hour or something, right? So then let's see what tension, because this is probably going to need a lot of tension. We need some industrial cable or something to pull this off. Now, this, for tension, is the first time that we need to consider the mass. And we simply will say then that the tension is equal to MA, which is just our given value of 2.2 kilograms times our centripetal acceleration. Okay? Now I'm not plugging it back into the original equation, right? But it's the same thing because I'm just carrying over. I'm just taking my calculated value of centripetal acceleration, v squared over r, and I'm just going to plug in that variable using Desmos. And you can see then that my value is 205 newtons. So pretty significant, right? Not too bad because it's not too massive of a ball. Okay? So that's the idea of calculating centripetal acceleration and, in this case, tension, but it could be any force, creating centripetal force. Okay? All right, well, I hope you come back for the second video for this lecture, talking more about circular motion, specifically planetary motion. And I hope this introduction to centripetal acceleration and centripetal force has been interesting and informative. Thank you so much for watching.